think about something really complex, maybe a modern airliner. Hundreds of thousands of parts, all these software systems, navigation, cabin pressure, everything.
Right.
Now imagine trying to get all those pieces working together perfectly.
It's a huge challenge.
Well, that kind of intricate puzzle, but in the world of software and sometimes hardware too, that's what we're digging into today. System integration testing, or SIT.
Exactly. It's really all about making sure the individual bits, software modules, maybe hardware elements, can talk to each other and, function together as one reliable system.
Because if one part stumbles.
The whole thing can get messed
Yeah.
up. Yeah.
So for this deep dive, we're looking at excerpts from a software system integration testing guide. It feels like a pretty structured expert view on this.
It is, yeah. Quite detailed.
And our mission, really, is to pull out the core ideas, the main methods of SIT, so you can get a clearer picture of how these complex systems actually get validated.
Makes sense.
So to kick things off, what exactly is system integration testing?
Okay, so SIT, System Integration Testing.
Mm-hmm.
It's basically testing that you do in an environment where software components are put together. And sometimes hardware comes into play too.
Okay.
The main goal is just to check that the whole integrated system behaves like it's supposed to, that it meets the requirements that were set out.
So it's not just about the individual pieces working alone?
No, not at all. It's specifically about checking their interactions, how they work together.
So less about whether one gear turns smoothly and more about whether all the gears mesh correctly and actually, drive the machine.
That's a great way to put it, yeah. It verifies those connections, the data flowing between different software modules, and it also checks if the system can sort of live alongside other systems it needs to interact with.
Right.
The guide mentions this process of taking software, maybe hardware pieces, combining them bit by bit, and testing as you build it up.
Incrementally.
Incrementally, okay.
And it clarifies, too, if you're only integrating software with other software, that's usually called SSIT software integration testing. Makes sense.
But when you bring physical hardware into the mix, then it becomes HSIT, hardware software integration testing. The key difference is that real hardware is part of the system you're testing.
Okay, got it. SSIT for software only, HSIT when hardware's involved. But why is this integration testing step so critical? It sounds like, well, a lot of work.
Oh, it's absolutely vital if you want to build systems that actually work reliably. The guide lays out some really crucial benefits.
Like what?
Well, first off, you find defects much earlier. By testing how components interact early on, you catch problems that you just wouldn't see if you only tested each piece by itself.
Right. Issues that only pop up when things try to talk to each other.
Exactly. And getting that feedback early helps developers know if their modules are actually, compatible. Imagine finding out two critical parts just don't fit together when the whole thing is almost built.
Yeah, that sounds like a nightmare scenario. SIT helps avoid that.
That's the goal. Catching a small mismatch early is way, way better than dealing with a massive system meltdown later.
Definitely. What else? Any other big advantages?
Yeah, it also gives you more flexibility in scheduling bug fixes. Because you're integrating and testing in stages. You can often fix issues as they come up, maybe even while other development is still going on.
Okay, so it's more manageable.
Right. And beyond that, SIT makes sure the data flows correctly, that control signals move between modules as expected. It verifies things like timing, memory usage, making sure the system operates within its limits.
And ultimately, it checks against the original requirements.
Precisely. It confirms the integrated system actually does what it was supposed to do according to the software requirements. For instance, SIT could catch if, say, a sudden flood of data overwhelms one module and causes slowdowns or crashes, something you wouldn't see testing it alone.
Okay, so we know what SIT is, why it's super important for making sure everything works together. Now, the practical side. How is it actually done? What are the approaches?
Well, the guide talks about a systematic way to build and test the system, specifically looking for those interface errors, the problems where components meet.
Makes sense.
And it contrasts two main methods. First, there's the Big Bang approach.
Big Bang. Sounds dramatic.
It kind of is. It basically means you wait until all the modules are supposedly ready, throw them all together at once, and then try to test the entire thing as one massive unit.
Wow. That sounds incredibly risky, like trying to assemble a 1,000-piece jigsaw puzzle by just dumping all the pieces on the table at the same time.
That's a perfect analogy, actually. And the guide really stresses the big problem here. If you find errors using Big Bang, figuring out where the problem started is Well, it's incredibly difficult.
Because everything is connected already.
Exactly. So many components interacting. Fixing one bug might just cause another one somewhere else. You can spend ages just trying to untangle a mess.
Yeah.
Weeks, maybe months, just debugging interconnected failures.
Okay, that definitely sounds like a developer's worst nightmare. So what's the more sensible alternative?
That would be the incremental approach, which the guide strongly favors.
Right. Piece by piece.
Exactly. You integrate and test the system in small, manageable chunks. This makes it so much easier to isolate errors when they pop up, because you've only added a few new things since the last test worked.
Much less guesswork involved.
Much less.
Yeah.
And it also lets you test the interfaces between these chunks more thoroughly. The guide also mentions that black box testing is a key technique used here.
Ah, black box testing. So focusing on inputs and outputs, the what it does, not the how inside.
Precisely. At this integration level, you're more concerned with whether the combined parts produce the expected results based on given inputs rather than digging into the internal code logic of each piece.
That makes sense. And the guide also mentions something about where the testing happens, the environment.
Yes, that's important. Initially, some testing might happen in what's called a host environment. That's basically a development system used to simulate how the final target environment, the actual hardware and operating system the software will run on, behaves.
A simulation.
Right. But, and the guide really emphasizes this, the final confirmation testing must happen on the actual target hardware.
Why is that so crucial?
Because there can be subtle issues specific to that environment. Things like weird memory allocation problems or how the software interacts with very specific hardware features. Things that just won't show up in a simulation.
Gotcha. You need the real deal for the final check.
Absolutely. And for really big projects, you might have several integration stages, starting more simulated and getting closer and closer to the actual target hardware as you go.
Okay, this incremental approach sounds way more logical, much less chaotic than the Big Bang. Now, the guide apparently breaks down this incremental idea into two main strategies, top-down and bottom-up. Let's maybe start with top-down.
Sure. So in the top-down approach, you begin the integration and testing right at the top level. That's usually the user interface or maybe the main control module of the whole system.
Starting with the boss, essentially.
Kinda, yeah. And the lower level parts, the ones that haven't been built or integrated yet, you simulate them using things called stubs.
Stubs.
Think of them like stand-ins, temporary replacements. They're little bits of code designed to mimic the basic inputs and outputs of the real modules that aren't there yet. This lets you test the logic of the higher level components.
Okay, so you use these fake pieces underneath.
Right. Then you start downwards, step by step, replacing those stubs with the actual finished modules as they become available. You can do this breadth first, integrating all the immediate subordinates before going deeper or depth first, maybe following one critical path all the way down.
So you're building and testing from the top, like maybe constructing a pyramid layer by layer from the peak downwards.
That's a good way to visualize it, yes.
What are the tricky parts or drawbacks with this top-down method?
Well, the guide points out a couple of main logistical challenges. One big one is that you often need some real processing happening at the lower levels to properly test the upper levels.
Because the stubs are just faking it.
Exactly. It can be hard to get realistic data flowing up through the system when the actual workhorses aren't there yet. And the other thing is creating good stubs, ones that accurately mimic what the real module will do, especially if it's complex. That can be quite difficult and time-consuming in itself.
Right. You might spend a lot of effort building these temporary stand-ins.
You could, yeah. It adds overhead.
Okay, that makes sense. You're almost predicting and coding the behavior of something that isn't fully there. Now let's flip it. What about the bottom-up approach?
Right. The bottom-up strategy. This one starts at the other end with the most basic, lowest-level modules in the system hierarchy.
Starting from the foundations.
Precisely. These low-level modules are typically grouped together into what the guide calls clusters. Each cluster performs some specific basic subfunction.
Okay.
To test these clusters, you use drivers. These are small, temporary programs that act like the higher-level modules will eventually. They feed test inputs into the cluster and then check the outputs to make sure the cluster works correctly.
So drivers push data in from above, while stubs pretend to be things below.
Exactly. Once a cluster is tested and working, you integrate it upwards with other tested clusters. As you move up the system, building bigger and bigger chunks, the need for those drivers starts to disappear because the real higher-level modules are being integrated and taking over that role.
So you're building from the ground up, making sure the basic blocks are solid before assembling the bigger structures. What are the main upsides here?
Well, a big advantage is that the actual processing power of the lower-level modules is always there when you need it. You don't have to deal with the complexity of writing stubs for those core functions.
Right, no faking the fundamentals.
Exactly. And the guide also notes you can sometimes combine approaches, maybe use bottom-up for most of the system, but then use a top-down approach for just the very top level or two. That can help reduce the number of drivers you need to write overall.
Ah, interesting. Like maybe test all the data crunching bits bottom up, then integrate them with the main controller tested top down.
Something like that, yeah. It could simplify things, potentially needing fewer drivers for those lower-level clusters if the top layers handle the interactions sooner.
Cool. So it sounds like both top down and bottom up have pros and cons, and maybe mixing them is often the smartest way. Now, the guide also spends some time specifically on hardware software integration testing, HSIT. What are the key things to think about when hardware gets involved?
Right, HSIT. This is specifically about testing the software components on the actual target hardware. The goal is to make sure the high-level functions work correctly in the real physical environment they're designed for.
So not just simulating anymore.
No, this is the real deal. Verifying the software's behavior running on the intended hardware. The guide calls it requirement-based hardware-software integration testing, meaning you're checking if the software on the hardware meets those high-level system requirements.
And what kinds of problems are especially likely to show up during HSIT? It feels like adding hardware adds a whole new layer of potential issues.
Oh, absolutely. It introduces a whole range of potential problems specific to that hardware-software boundary. You can get basic interface errors, of course.
Like the software sending the wrong command.
Yeah, or misinterpreting data coming from a sensor, but also things like violating how the software is supposed to be partitioned across different hardware bits. Or maybe the hardware's own self-tests fail to catch certain faults.
Right.
Or the system doesn't react properly if a piece of hardware does fail. The guide also lists errors related to timing and sequencing between hardware and software, problems handling sudden bursts of input transient loads, or even glitches from unstable power supplies.
Wow.
Incorrect behavior in feedback loops, where software actions affect hardware, which then affects software again. Memory management issues across hardware boundaries, fights for access to shared data buses, even problems with loading new software onto the hardware out in the field. It's a much, much more complex picture than just software talking to software.
That is a long list of potential pitfalls. It really drives home the extra complexity hardware brings. And the guide says all HSIT happens on the target hardware, using mostly black box testing.
That's right. Because you're dealing with the real physical stuff and how it behaves, you have to test in that real environment. And since the focus is on whether the whole system meets requirements from an external view, black box testing, checking inputs and outputs is usually the main approach.
Makes sense. The guide also mentions key things to consider when designing HSIT test cases. What are testers focused on?
Yeah, several vital aspects. They need to check if the software is correctly getting all the data from the hardware, handling the scaling and range of that data properly.
Like sensor readings.
Exactly. And conversely, is the software sending the right commands and data out to the hardware? They also need to test under normal conditions, but also push the boundaries abnormal conditions, extreme values.
Stress testing, kind of.
In a way, yes. How the system handles interrupts on the hardware is critical, though the guide suggests testing interrupt handling in isolation too. Timing is huge. Does the software react fast enough when interacting with the hardware?
Right.
Memory usage across the whole system, how the system transitions between different states, like from standby to active. These are all essential areas to cover thoroughly in HSIT.
Okay. Now, shifting gears just a bit, the guide also mentions software-to-software integration testing, SSIT, again, briefly. How does that differ in focus from HSIT?
Right, SSIT. As we touched on, this is about testing software components interacting with other software components, either in the development environment or maybe in the target hardware. But crucially, any other systems it talks to are usually simulated.
So software talking to simulated software, almost.
Yeah. The main goal is checking the high-level functionality, the communication protocols, making sure the data exchange between those software modules is correct. And again, the guide points out that the incremental approaches, top-down, bottom-up, or a mix, work just fine for SSIT too.
Got it. Now, something called the ETVX strategy comes up in the guide regarding integration testing. Can you unpack that for us?
Sure. ETVX, it's an acronym, stands for Entry Criteria, Task Validation, and Exit Criteria.
ETVX.
Okay, it's basically a structured way to define any testing phase. What needs to be ready before you start entry, what activities you actually do, task, how you check if things worked. Validation of the guide doesn't detail this part much, and what conditions mean you're finished. Exit.
A framework for the process.
Exactly. For integration testing, the entry criteria mentioned are things like unit testing needs to be finished for the individual modules you're about to integrate. You need the software requirements docs, the design document showing how it's built, the verification plan outlining the testing strategy, and specific integration documents explaining how modules fit together.
So all the groundwork needs to be done first.
Pretty much. You need the plans and the tested parts ready to go.
Okay, makes sense. What about the tasks or activities involved in SIT according to ETVX?
Right, the actual work. This involves creating the test cases themselves, based on both high-level requirements and the detailed low-level design. Writing out the test procedures, the step-by-step instructions.
Okay.
A big task is actually combining the modules into testable builds. Often you need to develop a test harness that's kind of a support structure of drivers, stubs, and maybe other tools to make testing easier.
Right, the scaffolding.
Yeah, good analogy.
Yeah.
Then, of course, running the tests on these integrated builds. As you integrate more pieces, you keep testing. And a really crucial step is rerunning all the relevant tests on the final target hardware platform.
Making sure it still works in the real environment.
Exactly, that final check.
And then the E and X exit criteria and outputs. What signifies that SIT is successfully completed?
So the exit criteria are basically the definition of done for SIT. According to the guide, this means you've successfully integrated all the software modules on the target hardware, and you've verified that the integrated software works correctly according to all its requirements.
So it's built and it works as specified.
That's the goal. And the outputs from this whole process are primarily the integration test reports documenting everything done, the results, any bugs found, and also the software test cases and procedures, SVCP themselves. They're valuable because you can reuse them later for regression testing if changes are made.
Okay, that ETVX framework provides a nice structure. Now, we sort of started here, but the guide circles back to the Big Bang approach near the end. What's the final word on that strategy?
Yeah, it basically just reiterates the point. Big Bang means integrating everything all at once, usually when all the parts are thought to be ready.
Which we established sounds pretty hairy.
Exactly. The guide repeats the main drawbacks.
Yeah.
It's extremely hard to find the root cause of failures because everything's tangled together and there's a much higher risk that serious bugs will slip through into the final product.
Not ideal.
Not at all. The conclusion is basically that you'd only really use Big Bang if you absolutely have to, maybe due to some really unusual project constraint. It's definitely not the recommended engineering approach.
Right. Stick to incremental if you possibly can.
That's the strong advice, yes.
Okay, so let's try to wrap up this deep dive on system integration testing. The big takeaway seems to be that SIT is this absolutely critical step for checking that different software modules, and often hardware too, can actually work together the way they're supposed to.
Absolutely. It's about ensuring the whole is greater or at least functional compared to the sum of its parts.
And that incremental approach, building and testing in smaller, manageable pieces, is generally way better, much less risky, than the all-at-once Big Bang method.
Definitely the preferred way. More control, easier debugging.
And within that incremental world, you've got strategies like top-down, starting from the user view, and bottom-up, building from the foundations. Each has its own, pluses and minuses, especially when you throw hardware into the equation with HSIT.
Precisely. SIT really is a cornerstone for building complex systems that you can actually rely on. It bridges that gap between components working fine on their own and a complete system that actually delivers what the user needs reliably.
Because you could have perfect parts, but if they don't connect right,
the whole thing can fail. Integration testing is what checks those connections.
it really makes you appreciate the complexity, doesn't it? Like, think about any sophisticated tech you use every day, your phone, maybe your car's infotainment system, online banking. Just imagine the sheer number of different software bits, maybe hardware components too, that had to be painstakingly integrated and tested just to make it feel seamless to you.
A huge amount of behind-the-scenes work.
Totally.
Hmm.
What kinds of weird, intricate problems do you think those engineers ran into just getting all those pieces to talk nicely to each other? It kind of highlights all that invisible effort that goes into making our tech dependable. Definitely something to think about.
It really is. That hidden complexity is everywhere.
Well, that gives us plenty to ponder until our next deep dive.
CTSS.